In this unit, we will study the natural numbers, denoted as set n. The principal objectives are to review the decimal number system, define the set of natural numbers, and examine their operations, along with their fundamental properties. The basic requirement that we ask for is the knowledge of the basic mathematical terminology, typically acquired during secondary education. The concept of numbers traces back to the origin of the human species, emerging from the necessity to count. All civilizations have employed numbers, which is why they have introduced distinct symbols and rules to facilitate calculations, counting, and measurements. These systems of symbols and rules are referred to as numbering systems, and as previously mentioned, each civilization has developed its own. The number 284, written in our system, can be represented in various other systems. In this chart, you can see it written in Egyptian, Hebrew, Maya, and different numbering systems. Our fundamental numbering system is the decimal system. While other numbering systems exist, the decimal system is predominantly used in practice. It's termed decimal because it relies on 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, each with its natural value. This system is a positional system. What does it mean to be a positional system? Well, the digit on the right in any number represents the units, while each position to the left signifies a multiple of a power of 10. To understand this, let's see an example. The number 248 is essentially 200 plus 40 plus 8, signifying 200s, 4 tens, and 8 units, 10 to the power of 0. So 8 represent units, 4 represent tens, and 2 represent hundreds. In the case of 3,457, once again, we have the same breakdown. The 3 represents the thousands, the 4 represents the hundreds, the 5 represents the tens, and the 7 represents the units. The set of natural numbers essentially consists of the numbers used for counting: 1, 2, 3, 4, 5, and so on. Some experts include 0, while others do not, in the set of natural numbers. In this unit and going forward, we will consider 0 to be included in the set of natural numbers, and we will assume that when counting, 0 is used to represent nothing to count. The operations introduced in the set of natural numbers are well known. There are 2, addition and multiplication. These operations are considered internal composition laws, which means that when we perform these operations on 2 natural numbers, the result is again a natural number. The first operation, as I mentioned earlier, is addition, denoted by the plus symbol. The second operation is multiplication, which can be denoted by either a dot in the middle or a cross. The numbers being operated upon are placed on both sides of the symbol, and in the case of addition, on both sides of the plus sign. One of the most notable properties of the set of natural numbers as we start is that 0 is considered an element of the natural numbers. This is a specific assumption we make in this unit. The fundamental property here is that if an element, a number, belongs to the set of natural numbers, then the next number is also in the set of natural numbers. Specifically, from the second condition, which is non-emptiness, it is deduced that the set is infinite. The fundamental properties of the set of natural numbers are listed in this table: the associative property, the commutative property, the existence of a neutral element, and the distributive property of multiplication with respect to addition. Regarding the associative property of addition, it states that when we have 3 numbers, A, B, and C, the result remains the same whether we add the first 2, and then the third, or if we add the second 2, and then the first one. In other words, the order of addition does not matter. This property allows us to extend the addition of 2 numbers to the addition of a finite set of numbers. We can add many numbers simultaneously. Similarly, the associative property of multiplication tells us that the order of multiplication does not matter. We can multiply the first 2 and then the third, or we can multiply the second 2 and then the first one with the same implications as in addition. The commutative property states that the order of addition and multiplication with only two numbers does not matter. The result is the same regardless of the order in which we multiply or add. In addition, A plus B is the same as B plus A. And in the case of multiplication, where A times B is equal to B times A, we have the well-known expression that the order of the factors does not change the product. Regarding the neutral element, we need to clarify a crucial point: the existence of the neutral element. The neutral element in addition is an element 0 that can be considered neutral regarding the operation. Adding 0 to any number leaves that number unchanged. A plus 0 equals A, and 0 plus A equals A, no modification occurs. Similarly, in multiplication, a neutral element for the product is a number that, when multiplied by any element, leaves that element unchanged. In the case of multiplication, this neutral element is 1. Therefore, A times 1 equals 1 times A, and indeed, it equals A. The neutral element is termed neutral because it doesn't bring about any modification to the operation. The concept of the neutral element leads to the existence of the next property, which is the inverse element. However, it's important to note that this property does not exist within the realm of natural numbers. No natural number, except for 0, has a symmetric element in addition, and no natural numbers, except for 1, have a symmetric element in multiplication. This is why, within the context of natural numbers, we can disregard this property. However, there is an important property, the distributive property of multiplication with respect to addition. This property explains how multiplication behaves in relation to addition. It means that if I multiply a number by a sum, how can I perform this operation? Well, it's quite simple. The element that is being multiplied multiplies the first term in the sum, and then it multiplies the second term outside the sum. This rule can be generalized based on the previously mentioned properties to any type of operation involving more than two sums or more than one factor. Well, before we conclude, let's briefly review what we've covered in this unit. First, we recalled the decimal number system. We have talked about the definition of natural numbers and their fundamental operations, along with the properties that these operations exhibit in the context of natural numbers. This is all. Thank you very much.